Welcome to video 6.2a wave phenomena. Let's start with the FET video that we've had before. Let's have it so that one end fixed and the other end we will send a pulse through. You can see that as the pulse goes down, it hits the clamp and then comes back. Let's increase the amplitude a little bit so that we can see what happens when it comes back. Notice that as it comes back, the amplitude no longer is at the top of this string, but it's at the bottom. That's because of Newton's third law. When the particles get to the clamp, when the energy gets to the clamp rather, the particles, the green and red particles right here, are pushing up on the clamp, so the clamp pushes them back down. If we change this to a loose end, we can see that we have a little bit different situation. When it gets to the end, rather than this ring staying steady and forcing the particles to go down, it moves up so that when the waves come back, they do not flip on the other side. Reflection is, as its name suggests, it's when waves bounce off a surface. And sometimes we have really nice clear reflection like we do off of a mirror or off of glass, or even a car for that matter in some places. Other times we have really rough, just a glare that is also oftentimes off of a car. And that's dependent on the surface that the wave is reflecting off of. When we're talking about reflection, the important thing to realize is if a light wave or any wave comes in to hit a surface at some angle, theta sub I, the incident angle, it is going to reflect off at an angle that is equal to that. So the angle of reflection is equal to the angle of incidence, and that is called the law of reflection. Now let's take a look at what happens to a wave on a string as it goes from a thinner piece of string to a fatter piece of string. We are back at Dr. Russell's animations from his webpage at Penn State rather. And so we notice if we look just at this top one here, we have a wave coming in. It has a certain amplitude. It hits this boundary between the thin and the thick wave, and the amplitude gets smaller. The reason that the amplitude of the wave on top gets smaller is because you'll also notice that not all of the energy gets transmitted through, some of it gets reflected. And that reflected energy is what makes the amplitude decrease. You'll also notice that because the string that it's going into is thicker and denser, you have a change of speed here. So we go from a high speed to a low speed because we were at low density and we've gone to high density. If we look at the opposite situation, a little bit lower on the page here, we have the string being thicker at the beginning and then thinner afterwards. Notice that the reflection here does not change its size. That's because this acts as a loose end and it's able to move up the thinner, less dense string so that the reflected string is on the same side of it. It does have a smaller amplitude again because most of the energy is going to be transmitted through. You'll also notice that the amplitude of the transmitted wave is a little bit bigger than the initial wave, not because it has changed any characteristics per se. We haven't added energy there, but because it has a thinner string to go through, it can have a higher amplitude. So this is when the wave also goes from a low speed to a high speed, and this is when the material that it's going through is higher density to lower density. This has to occur, these speed changes have to occur in order for the equation V equals F lambda to still work. Now let's look what happens if we have two wavefronts approaching each other, like here in part A, where one is at the top of the string and one is at the bottom of the string. As they approach each other, at some point in time, those two wave pulses are going to be at precisely overlapping each other. And that's when we get what we call superpositioning. And when we have situations of superpositioning, what that tells us is that the displacement of the particles is the sum of the individual displacements. Keeping in mind that the waves particles are moving some upwards and some downwards. So these wave pulses that are in the positive direction towards a crest, those displacements would be positive. And these displacements going to a trough would be negative, which is why for side A here, when the pulses completely overlap each other, it looks like there's no wave there at all because the positives and the negatives have canceled and the string doesn't move. Once the pulses have passed each other, you can tell that the lower wave is still the same and the upper wave is still the same. There's no difference between them, even though here it looks like they went away. This is an example of destructive interference, when the final amplitude is less than either of the originals. This could be all the way down to 0 as it is here, or it could be somewhere in between the top and the bottom amplitudes. If we look at B, B is a little bit different situation because both wave pulses are at the top to begin with as they approach each other. As they do approach each other and they get to the point where they overlap, notice that their amplitude adds to become twice as large if we make the assumption that these are the same height. This is constructive interference. So this is when the final amplitude increases. It doesn't have to add up to be the total of the both of them. Depending on where they are as they go over each other, you can see some partial constructive interference or some destructive interference, or a little bit of both. Okay, in this interference simulation here, it appears that we have wave A plus wave B is equal to wave C, where wave A is blue and wave B is red. On the picture here, if I stop it for a minute, we can't really see the blue wave at all. And that's because wave A and B have the same speed, the same amplitude, the same wavelength, and they are not offset from each other. So let me just change the amplitude of the blue wave some so we can actually see it and we can tell that it's there. This is an example of constructive interference because the 0 points line up with each other, the crests are at the same point, the troughs are at the same point. The superpositioned white wave is going to be the addition of the crest amplitudes, and it's going to be quite large. However, if we change the offset a little bit, let's make it so A and B are not moving at the same time. So let's say maybe A started before B did. Now you can see that at this point here, the amplitude is still going up because you've still got positive amplitude and a positive amplitude. But at this point, where the red wave, wave B, has reached the rest point, but wave A has not, the amplitude of the superpositioned wave is just that of B. You can reset that so that they are basically leaving at the same time. But now let's change A's wavelength. Because the situation we had before was showing constructive interference and it was still producing a really nice wave. But if you have two waves that are interfering with each other that are not the same wavelength or the same amplitude, you can see that it really goes crazy here. The blue and the red wave are still moving along in the background, but the white wave increases its amplitude and decreases its amplitude depending on the crests and the troughs are in relation to each other. Sometimes when you have interference between two waves, it doesn't look like this crazy situation where the superpositioned wave is moving and it has a bizarre format to it. Sometimes it looks like it's not moving at all. So let's take a look at those situations. So in this animation from the University of New South Wales, we have a string and we have some waves moving along on it. If we take a look at this more carefully, the blue and the green waves are our waves that are interfering, and the red wave is the superpositioned wave. Notice that the green wave is moving to the right, the blue wave is moving to the left. You can see that the red wave, the crests and troughs just seem to be sitting in one spot. And if we look at this point here, that part of the red wave does not seem to be moving at all. So while the green and the blue waves are moving in opposite directions, the red wave seems to be standing still, thus the name of a standing wave. We have special names for these places where the string's not moving or the wave's not moving, and these areas that are alternating between maxima and minima. In this particular simulation, the speeds of the waves aren't very large so that you can see the red going up and down in various spots. If we take a look at a still picture of this, and let's assume that it's actually multiple pictures on top of one another, you can see that we have the maximum, we have the minimum, and then with these lighter pictures of what it would be like in between. When we are vibrating our hand here and we're looking at what's going on, if we vibrate our hand a certain amount, we're going to end up with what looks like a half a wavelength of a wave here, with the maximum point called the antinode and the minimum point the point that doesn't move called the node. So nodes are places that are at rest on a standing wave. Whereas the antinodes are the maximum and minima of the standing waves. Depending on how much we vibrate our hand here, how rapidly we vibrate our hand here, will determine whether we have just half a wavelength of wave showing, or we have an entire wavelength, or as we see in picture C, we have 1.5 wavelengths. Each time we change the frequency of our source, it's going to change what our standing wave looks like. And the waves are not being destroyed, or energy is not being lost. Remember, it's still there in the form of the elastic potential energy in the string and the kinetic energy of the particles that are moving within the string as they are the particles and the energy is being moved back and forth. We just can't see it moving any longer. The next phenomena that we need to look at is called refraction. Refraction is the bending of waves at a boundary. So if we have an example of people and we have a row of soldiers, we have a column of soldiers that are marching to battle. As they go from being on solid, firm ground to going into mud, as the first wave front, this first row hits, every time a soldier hits the mud, he's going to slow down. Every single one of these soldiers will have to slow down when they get to the mud because it's harder to travel through. So the result is that the distance between each wave front, or the wavelength, is going to decrease, as is the direction going to change. So the direction changes and the wavelength changes. Well, if that's happening, then we must also have a change in speed. So refraction with the bending of wave at a boundary causes the speed to change. Frequency is not changing because the source, the energy the soldier is putting in, is staying the same. If we look at this picture over here, this is what it would look like for, say, a light wave going from, say, air into water. As the light ray hits water, some of it is reflected back. We're just ignoring that part to begin with. So that is our incident angle, and there would be a reflected angle. But with refraction, if we concentrate on the stuff that gets through, the incident angle and the refracted angle are going to be different. So in this case, theta 1 is not equal to theta 2 because your medium are different, and it is harder to travel through water than it is to travel through air. So the law of refraction says that the speed has to change when you go through boundaries that have different densities because the wavelength changes and the frequency does not change. And this law of refraction works both ways. This bending of the angle towards the normal occurs when you go from air to water. If we were to reverse the direction that we were looking at and say we had a flashlight underwater and we were shooting it up towards the surface, the light would go here and then it would bend away from this line here called the normal. The normal is a perpendicular line from the surface of the material upwards. And when you go from a more dense to a less dense situation, your angle is going to increase. So it works both ways. The last phenomena I want to talk about is diffraction. Diffraction really is the spreading of waves around an obstacle. This is what allows us to hear around a corner as well as to tell if a light is on in a room around the corner. Because what happens is if you look here, you have the wavefronts coming in all nice and parallel. You get to this block, and then you end up with this area back here that is really not being disturbed at all. However, it is here. So it's not like there's another source at this point that is creating more waves. What's happening is this wave, when it gets to the corner, is spreading out a little, and that continues, that wavefront continues to spread towards that point. Similarly, on the other side, it goes the same way. A short wavelength going through a passing log, and you've got a pretty big section of undisturbed area. But if you have a long wavelength that's passing that same log, you're going to have a relatively smaller area because the wavelengths, as they come around, are going to spread more the longer the wavelength it is. So those are the phenomena that go with the wave characteristics and the wave that we've been talking about so far. Bye.